Hi everybody, my name is Tim Brothers and I am the member of the Pepperell Democratic Town Committee who is sponsoring tonight's event. We thank you for attending our first of our new speaker series that will be focusing on issues that affect people in Pepperell and the surrounding community. We are very fortunate to have Dr. Benjamin Brown Steiner. He is a postdoctoral associate at the MIT Center for Global Change Science who studies atmospheric chemistry, including ozone, aerosols, emissions, pollution, and air quality. He studies climate science by running simulations with state-of-the-art climate and chemistry models. His primary focus is on uncertainty quantification, in which he tries to figure out exactly how much scientists don't know and how likely they are to draw an incorrect conclusion. He will discuss the difference between weather and climate and highlight some of the ways that global changes will impact the people and environment in and around the town of Pepperell. Tonight's talk will run about an hour, and we will leave 10 minutes at the end for questions. If you have a question in between, just raise your hand. We'll try to get to you. And if you'd like to know more about the Pepperell Democratic Town Committee, feel free to talk to Tom McGrath or visit our Facebook page and find out more about we have some more upcoming events later this year. All right, thank you, and give it to Ben.
Well, first, I want to thank you for having me. I do a lot of science and I talk with a lot of scientists, and that's rewarding in one way, but it's not the entire conversation that I like to be having. So talking with communities like this is a really rewarding way for me to kind of make my science mean more than just the papers that I get out. And this picture is not anything more than just a particular day's worth of snow. It's not indicative of the future of Pepperell, but I just thought it was a good picture. So I'm going to talk about, this is kind of the outline I'll do, and I'm happy to answer questions, especially if they're clarification questions throughout, but if they're bigger questions, I like to say that for the end for kind of a more discussion type thing that I have planned. But first, I'm going to talk a little bit about facts versus values from a scientific perspective, and I found this is a good way to start these presentations to kind of show exactly where I'm coming from and what I'm speaking to and what I'm not particularly speaking to. That's about 5 minutes at the beginning. Then I talk about weather versus climate, which is one of the sticking points that I think really makes it difficult to have productive conversations with people. Talk about weather events, but they're drawing conclusions about climate events, and there's a really big difference there. And we'll spend maybe 10 minutes making that really intuitively clear what the difference is. And then I'll spend about 10 minutes talking about the current state of global climate science, global climate change science. That's a small piece of it, because the brunt of the presentation will be talking about regional climate change here in Pepperell. Natural world. Science is two things. It's the study of, and it's the body of knowledge you gain. So scientists often are just looking at the world. They're observing the observable world and drawing conclusions based on that. And that's what I do a lot of. I use observations and I run models, and that's what I'm doing. The other piece of it is this body of knowledge that's been built up over the decades and centuries that humans have been gathering knowledge. And it includes everything from mathematics and logic at the very bottom up to the more specific ones. And as you move through science, you tend to learn the basics of physics and chemistry, and as you work your way up, you pick a discipline, and you learn all there is to know about that discipline. So as an example of this, these are the textbooks that I've gathered over my scientific career, starting at the bottom with the calculus and chemistry I did as an undergraduate when I was doing environmental engineering. And as I went up, it's specified to atmospheric chemistry and physics, and then some more math, and then some more chemistry, and then some more math. And it really, these top ones here are very specific to my field. And that's what my main expertise is in atmospheric chemistry and climate change. I have worked with a lot of colleagues in different disciplines, so I have connections to them, but my little tower is the atmospheric chemistry tower. And I want to make this point because this is, a lot of my colleagues don't do a whole lot of scientific communication, or it's difficult if you haven't done a fair amount of it. And this is kind of my favorite explanation to how that works. If this is the total body of what humans know about the natural world, when you're in elementary school and middle school, you learn a little bit about everything, kind of at the beginning. You go to high school, you learn a little bit more about everything in a generalized sense. If you go farther than that, you usually pick a discipline. So you learn more, but you get a little bump on the side. That's your discipline that you're learning about. If you do an advanced degree, or this is really, if you're becoming an expert in any particular field, what you tend to do is you build it, for a master's and a PhD, try to build it up to the edge of the boundary of what humans know. And I'm going to zoom in on this section right now, because this is really what a PhD is. When I got my PhD, I pushed up against this boundary, and after 6 or 7 years,
I added a little pimple to that outside of the knowledge. And that pimple is what an advanced degree is, a PhD is just that little pimple. But the trick is, while you're doing that, your job is your entire world is supposed to be that little pimple. And so this is what I added, this is all the boundaries around it. My entire universe was those subdisciplines and the language that I used. That was my entire world. And it's hard then to speak to people from different communities because you've been thinking about this for 5 or 6 or 7 years, when really there's a whole world of knowledge that is different. And that's why I like doing these things, kind of expand it and branch out a little bit. So that's the PhD here. But also there's that whole PhD, the whole body of human knowledge is really a circle that's facts. Facts about the natural world that is observable and that we know. There's another circle that's important in this type of discussion, and that's values. So you can believe in things and believe things are good, and then you can know things and have facts, and there's a difference there. And really what I want to make the point is that this climate change issue is really somewhere in the middle where it involves facts and values, and where they overlap in a productive way, you get knowledge and actual wisdom. And this is where really decisions and actions are made in the middle here. You can't make them with just facts, and you can't make them with just values. You can, but they might not be the best decisions. It's really when they're working together here in the middle that you get the real wise and good decisions. But one thing that scientists do a lot is they talk about uncertainties. And uncertainties in a scientific world mean very specific things. This is in the scientific fact circle here. There's things that we're very certain about, and there are things that we're uncertain about. And the act of us doing science is us trying to expand this knowledge and make things that are uncertain more certain. So for instance, this is a carbon dioxide molecule. We know it's 1 carbon and 2 oxygens. We know that structure very well, what it does, its behavior. That's very much in the very certain part of the scientific body of knowledge. If we're wanting to know what's the carbon dioxide level in the middle of the atmosphere on July of 2009, we have satellites up that can kind of give us a view of that. They're not perfect, they don't have perfect coverage, but we have a better idea. We have a pretty good idea of what that is. So that's more farther out from the center, but it's still a very certain thing that we know. If we want to know what the carbon dioxide level was 800,000 years ago, no one was there to observe it, but we do have alternate ways to get that. These are ice cores that give us some idea of what's happening there. So the carbon dioxide level 800,000 years ago, we know it, but it's less certain, because maybe that particular bubble was influenced by one thing, or that ice core was influenced, so that's farther out in the circle. And then there's this. You might have seen some of these figures. This is temperature, historical, and then into the future under different scenarios. And these future scenarios, scientists use them because they don't know what humans are going to decide to do. That's not a thing that science can figure out. So this whole what is humanity going to do in 2100, that's kind of in the middle here, where there's uncertainties in the science, there's uncertainties in what people are going to decide to do, and that's often where a lot of these debates happen. And they happen, they're particularly troublesome when there are uncertain parts of science, like exactly how much is the Earth going to warm if we double carbon dioxide levels. We have a good idea, but that's not terribly certain. So when the debate's about what we should do to prevent the worst climate change, it's really in this more muddy realm, mixing science and values and beliefs, and that's why this debate often it can be pretty contentious at times. So I'm speaking to the facts side. That's what I'm here to do. It's up to you to kind of come up for your community what you want to do and what you value to respond to these facts. So, does that make sense? I kind of like that distinction, and I like talking about that. So, all right. Next part here, about 10 minutes. I want you to get in your mind real quick, what is weather? When you experience weather, what do you see in your mind when you have weather? And it's usually weather maps or storms. Usually it's how hot you are or how cold you are, how wet you are, and what's going to happen tomorrow. Weather's a very short-term thing, temperatures and precipitation. The forecast for the next 2 days, that's important for us to know for weather. I want you to think about what's climate. How do you experience climate? And climate is usually much more abstract. It's probably figures like this that you maybe understand partially. There's different climate zones in the globe that's definitely climate. Polar bears or seasons, or climate's more abstract. Maybe it's a person or an idea or a diagram. Climate's more difficult to grasp because, first of all, we all experience weather. Every day we go outside, we experience weather that's very close to us. And I am a big fan of Calvin and Hobbes. And the father from Calvin and Hobbes loved experiencing bad weather. He was a big bad weather guy, rain or snow or sleet, he really enjoyed it. In this particular panel here, Calvin comes and asks his mother, "What's the weather like outside today?" And she snarkily replies, "Well, go step outside and see." Because you can do that. You can step outside and experience the weather. But what if Calvin instead asked, "What's the climate like outside today?" She couldn't really answer that. There's not really an answer for what today's climate's like, because no one ever experiences climate. You can never step outside and get a feeling for the climate of the moment. And I'm going to try to make this really intuitive for these next few slides here. So this is from where I was in Ithaca, New York for several years. So this is January of 2015 all the way to February of 2016. So it's just over a year's worth of temperature data. Red is the daily high, blue is the daily low, and yellow is the average for that day. And I'm going to focus in on the winter time period here. But so weather, this is weather, it's variable. It has a lot of wiggles, it goes up and down, that's what weather is. When we think about the climate, we think about this much more smooth pattern in the middle. So we know that summertime is warmer than wintertime, but there are some summer days that are, as low as some of the winter highs. So it's not an absolute thing that weather is going to be exactly the same as climate. I'm going to focus, like I said, on January to February of 2015 and 2016. And for us in Ithaca, and I know this was a bad winter for you guys here too, it was pretty snowy in Ithaca. It was a little bit warm, but there was a lot of snow. While this year, it was actually colder, but we didn't have a whole lot of snow. It was not a snowy year. And so I'm trying to think, were either of these normal winters? Or what's a normal winter to have? And I'm going to zoom in on these here. This is 2016. This is just January and February. Again, the high temperature, the low temperature, and then the yellow is the average. And this particular day, weather's wiggly. It goes up and down, especially see at the end, it's the cold front, warm front, cold front, warm. That's what weather does. There was a very strong cold snap that the low was almost 10 degrees below zero that one day. I remember that day very well because I experienced weather. It was very cold. What I have here, I'm counting up here the number of days that are higher than 60 degrees and the number of days that are below 0 degrees as my extremes. Things I'll probably remember about that year are those extreme days. So I have the count going up there. So I want to compare 2016 to 2015. Were either of these normal winters? They're different. They have different characteristics. They're wiggly, but it's hard to tell from these two what a normal winter would be. I'm going to go back in time now to 2014 and 2013 and 2012. And as you go back, you can kind of see that weather is definitely wiggly. There's not a normal pattern there. It's a highly variable system going back to 2006. And then you can see here, if I'm trying to remember the warmest and the coldest days, there's not really a pattern there, or it's very random, because those are very random parts of the weather. So my intuition for whether 2006 was a warm or cold winter, there was 2 warm days, no cold days, but there were cold days, and it was kind of the average. My intuition for this is not very solid. And this is when we turn to the climate perspective to kind of get an idea of what a normal winter would be. So again, here's 2016, and here's 2015. And I'm going to average the two of them together to get a 2-year climate. And I want to point out again the really cold snap that was here, because it's going to show up a little bit later. But when you average those 2 years together, you get this. So it's a little bit less wiggly than each individual year. In this case, you do get that cold snap. It appears in the 2-year average because it was a very extreme cold snap. But what if we go back farther? This is a 5-year average. And you see again now the cold snap is averaged out in the 5-year climate. And the variability, the expanse of it has shrunk a little bit more. If you go back 11 years, it shrinks even more. And then if you go back 21 years, it shrinks even further. And when we're talking about climate, we're really talking about at least 20 years of averages. So a weather event that happens today, you have to consider that as an average along with the last 20 years or the next 20 years to really be talking about the climate piece of it. So what's the normal winter for Ithaca in January and February? You can expect the average temperature to be kind of in that band right there. That's a normal temperature. If the temperature is up a little bit higher or a little bit lower, that's also normal. Weather's variable. And then the cold snap like this that we had that I remember, that was a truly exceptional weather event, but it's still just weather. It's really hard to draw a climate conclusion about a single event, even though it's very memorable. And then when we're thinking about changes into the future or how the climate is changing, we're talking about, a degree or two over the next 50 years or 100 years. We're talking about relatively small changes in the climate. And this cold snap, if it happened in 2080, would still be shifted up just a little bit. So it'll still be extremely cold. It won't be quite as cold. Or if you flip it and it's a heat wave, a really hot day, or a drought, it'll be a little bit worse, but it'll still be kind of in that band of variability. So I want you to think about now when you get in debates maybe, and someone is talking about weather or refuting climate change because it was cold in the wintertime. That's really not, you're not talking about the same things. And I think it's really important to be able to at least slow down and kind of think about it that way, because we don't experience the climate. We really need to abstract it in this way, and that's why you really need to look at the data on the long term. So that's that piece. Now I'm going to review real quick just the state of global climate change right now, kind of what's the newest and the most advanced stuff. And has anyone seen this figure before? Yeah, this is used all the time in my field because it's chaotic, but it summarizes everything really in a nice nutshell. And what it shows here, the line in the middle is 0 degrees, 0 degree change. And each of these bars is the amount of warming that happens based on different species that are emitted. So at the very top here is carbon dioxide. Carbon dioxide is the largest warmer that we have. It's warming us here. This bar here goes out to about 1.5 watts per meter squared. And a watts per meter squared is what we use to talk about the warming of the planet. And to think about that unit, 1 watt per meter squared is 1 extra Christmas light on every square meter of the entire globe, roughly. That's about 1 watt per square meter. So carbon dioxide, since the pre-industrial times, has added about 1.5, almost 2 Christmas lights to every square meter of the entire globe. That's kind of the warming that we're talking about there, which is not a whole lot of warming when you get down to it, especially, weather is very variable. We're talking about a relatively small change, but we're seeing the impacts of those type of changes. And this kind of summarizes a lot of the other species. I want to point out there's some things that we're more uncertain about. This one here is aerosols, which is little floating particles of dust and soot and salt, how they affect clouds. And what aerosols do to clouds is they tend to make clouds smaller and brighter, which tends to cool the climate instead of warm the climate. So we have here, the bar is negative, but this error bar, the kind of their assessment of uncertainty, is very large. This is one thing that's very important. It's a relatively large bar, but we're more uncertain about it. We need a lot more research to figure out exactly what clouds are doing. You can see the error bar for some of these are small because we're pretty certain. We're very certain about some of these. This is a very large error bar here. So in a nutshell, if you on the first order, if you want to think about climate change, it's carbon dioxide, it's methane. These aerosols and clouds are important, and we need more work in this stuff. But in total, since 1750, we've added about 2 Christmas lights to every square meter of the entire globe. That's the level of warming that we're talking about right now. And that's just present day. What if we're looking into the future? So this is another figure. You might have seen parts of this. It's 1850 on the left all the way to 2300 in this particular case. The center here is present day. And so these are our best estimate of historical values for temperature that we know. And these are some of those different scenarios. They renamed them for this figure, but these are different scenarios out to 2100, 2200, and 2300. And I want to point out here definitely, well, first we have the different scenarios because we don't know what humans are going to do. But this scenario here, this is pretty much the business as usual scenario if we don't enact any policy, is most extreme, and it's really uncertain out to 2300. It's kind of silly to run a model out to 2300 because the world's totally different then. Who knows what the world will be in 250 years, but this is kind of the best guess for it. And I want to point out here, this is the temperature change that we might expect if this is what humans decide to do. And these here, the highest one here is about 12 degrees Celsius. That is extreme. That is a world that we don't really know. It's not as likely as 8 degrees, but it's not impossible. And then if we do enact some policies, we can kind of get down to some of these ranges. It's very hard to get below this 2 degree level. That's kind of a present state where if we pass 2 degrees, things are going to change in ways that we don't quite understand. So we don't want to go above 2 degrees. All these scenarios, there's very few of them that are below that. And this particular one, the lowest one, actually involves us sucking carbon dioxide out of the atmosphere and put it in the ground. So it's really not a likely scenario. So at this point, what we're looking at is at least 2-degree warming, with a fair amount of uncertainty, but 2 degrees plus. And then most recently, there was the Paris Agreement and all these international negotiations. This is kind of the end product of what happened at Paris, where again, this is 1990 to up to 2030 in this case. The blue one, is kind of the business as usual. If no one does anything and we keep going, that's what the blue is. These lines here are what we would need to get to 2 degrees or to 1.5 degrees if we want to go even farther. And if all of the countries that promised to do things in the Paris Agreement did what they promised to do, that's what the pink line is here. So we've promised some things and we're doing action, but it's not matching up with our goals. Their goals are 1.5 to 2 degrees. So we need more work to get down to where we want to be. And that's kind of there's still debate about exactly what the magnitude of these changes are, but it's definitely sure that it's good that we're doing stuff, but it's not nearly enough. And we're going to have to keep revisiting this if we want to actually avoid that 2-degree warming where we're going. So that's the current policy aspects of this. I also want to show this. This is a nice figure. This is what I do a lot of modeling work, and this is a really nice way of looking at what models can do for us. Where this is 1980 out to 2030 again, 50 years. The black lines are observations, kind of collected all over the place, but averaged together. And you can see there's variability again. You know, it's weather, it's varying year to year. The orange here is a model run that was kind of tuned to the period and matched the observations. And now we're pretty confident it's getting what happened in the past. And now, looking into the future, you know, we don't know exactly what's going to happen. We don't know when the next El Nino is going to happen, or we don't know when a volcano is going to erupt. So you have to come up with these scenarios to kind of figure out what might happen. And so you can see, you know, there are certain things that this model has said is going to happen, and you get these weird little wiggles. What's nice about this is in a model, because you've made it and built it, you can look at the individual parts and figure out what's going on. So in this case, these are the different forcings, we call them. This is the change from the average. So the center of both of these is at 0. And the purple one is ENSO. That's the El Nino cycle. And so we know it has big swings up and down. Doesn't happen every year. Kind of happens in a weird cycle. But that's the ENSO signal. So in this scenario, they kind of duplicated this pattern out in about 2020. They said, well, maybe there'll be a big El Nino year in 2020. The blue line is volcanoes. Every time a volcano erupts, you get global cooling for a year or two because of the aerosols or the stratosphere, it cools, but they eventually fall out and it gets back to normal. So they're saying, well, there'll be a volcano eruption in 2015. This paper's old now. We didn't have the eruption in 2015, but that was kind of what their guess was. This greenish color is the solar cycle, the influence of solar activity on global climate change. And there's definitely an influence, but it's relatively small. And it's relatively predictable. The sun is a very predictable cycle. So this is the solar influence. And then this one here is the human influence, what humans have been adding to the system. And this is also, we have a pretty good idea of what we're spewing into the atmosphere. And our influence is just this steady increase over time. So even though there are these variable cycles, there's El Nino and the volcanoes and everything, this is really the driving trend. And when you look back at the total trend, you know, you can see the El Nino years, you can see the volcanoes, but the dominant trend at this point is the human influence, the warming. So I like picturing it this way because this is what models let us do. You can't figure out exactly what's going on. Is this all El Nino and all volcano in the past? Because we just have a temperature record. We don't have necessarily all the information, but when we're looking into the future, we can kind of piece it together and figure it out that way. So that's temperature trends. I might skip this for now. I'll talk about sea level rise a bit at the end. But I just want to make the point here that as we warm the atmosphere transfers heat into the oceans at a particular rate. And the ocean is this big heat sink that takes hundreds of years to kind of balance out. So it absorbs heat from the atmosphere. It then gets cycled down, and in maybe 100, 200, or even more years, it'll then eventually reach this equilibrium state. And so that's partly why this is a kind of a confusing part of climate science, because we're not seeing necessarily as much heating as we would have expected. And we think it's because the oceans are taking up more heat than we initially expected as well. And when oceans warm, when they take up heat and they warm, they expand a little bit. That's a very basic nature of water physics. And that's why we see most of the sea level rise. And really what I want to point out here is this is another one that goes out to 2500, a crazy amount of time in the future. But these changes that we're causing, they happen slowly. This is 2000 and this is 2050. And we don't see hardly any change there because of this slow rate of heat absorption in the ocean. But once it starts, it really tends to take over. So by the year 2100, this looks like, oh, maybe about a meter in this particular case. I mean, that's a lot, but it's not as much as it's going to happen by 2200 or all the way up to 2500. You know, once we start this process, we've kind of put into motion this sea level rise that is almost impossible to stop because of the slow equilibrium of the ocean. So I'll talk about sea level rise a little bit more when we get to the pepperell stuff at the end, actually, which is right now. So now I'm going to look at kind of climate change in pepperell at the regional scale. And I looked up online, kind of looking at what the present climate in pepperell is, and it seems like it is a little bit more rainy than average. It is a little bit less sunny than average, maybe a little bit more snowy than average. And I looked up, there was an assessment of the natural disasters that have happened here, and most of them seem to be water related. Floods and storms and hurricanes and storms and blizzards and snows. So it seems like pepperell is they're tied to water pretty closely. And I, from my few discussions, I think that's a pretty safe assessment that pepperell is a water sensitive area. So I'm going to be focusing mostly on water changes and precipitation changes. And I want to make the point, this is kind of tricky for a global model standpoint because we're talking about a very small area in a global sense. And global models have trouble identifying regional changes, and I'll show why here. This is a picture of clouds from space. I like clouds, so this is why I use this example. But this is about maybe a 400 by 400 mile picture of clouds, where we have cumulus clouds here, there's the ocean below it, there's something going on here, there's this front here with stratus clouds. There's a lot of detail in this particular grid box. And if I was to model it and want to like really get all the details right, maybe I'll choose a resolution like this and say, well, here's the front, and here's the stratus clouds, and here's some of the detail, and here's some of those storms. This would be an adequate representation of all of the detail that's happening in this cloud field. But this is a really computationally expensive way to run a global model at this resolution. So we have to then say, well, let's reduce the resolution some amount, maybe to this. And this is not the same, this is a different view of what's really happening in the clouds. This is also too high. Really, a lot of what the global models do have to be this much more coarse scale representation, where we do have kind of the average cloudiness in each grid box, but we lose a lot of that detail. And we call it parameterized. We have to add that in kind of a mathematical way, so that if there are, in this case, convective storms, we know they're moving heat from the surface up high. But these grid boxes don't resolve those convective storms. We have to add equations to kind of do that for us. So that's one of the challenges. This is the global climate view, the global model view, and this is the reality. And they're close, but it's different. And that's the trouble that we're having here, talking about regional climate in general. Right. So this is the current state of global models. The top left there is kind of state of the art for the last 5 or 10 years or so. And these are all the examples of how we're advancing and how we're getting better grids. This is kind of what we hope in the next 10 years or so. And then there's some models that have these nested grids where we're zooming in on particular areas. If we really care, in this case, about the central US, we can run the global model at the coarse resolution, but zoom in on the area we care about. And this is easier to do than running this resolution for the entire globe. And I want to give a practical example in my research about this here. So this is the temperature that I simulated for August 1st of 2001. Just an example of what I use. And this is how I often look at the data. It's this averaged view. We smooth some of the edges so we can kind of see some of the detail. But really, this is you might not see the difference all that well back there, but this is a gridded view, and this is the smooth view, the average view. So this is really how the model sees the world. In this particular case, which is standard for my global climate models, is considered at this point a relatively coarse resolution. It has 96 latitudes, it has 144 longitudes, and it has 56 vertical levels. So that's almost 750,000 data points for every variable, for every time step. And the time step here is a half hour. So this is a lot of data to have. And I can very easily run a simulation and get terabytes of data. And collectively in my group, it's very easy for us to produce petabytes. So a petabyte is 1,000,000 gigabytes. It's very easy for us to fill up our computers with this data, even at this coarse resolution. So when you're looking at the global climate, it's really hard to zoom into the regional details, partly because the computers aren't quite good enough. We don't have enough space, we don't have enough speed. But also, if we want to run multiple simulations for hundreds of years, we can't do it at the finest resolution across the globe, especially because, if I get a grant to study Eastern US, I don't particularly care what's happening in the center of Antarctica. That's not the focus of my study. It doesn't make sense to simulate that at the highest level of detail. So these are some of the trade-offs that we have to make. And for my model here, I'm going to zoom in a little bit. This is now the US at the grid that we use. You can look, here's Long Island, here's Cape. So we're in here somewhere. I'm going to zoom in a little bit more to kind of see where Pepperell is. This is another zoom in. Again, the Massachusetts is right about here. Here's the states. And so you can see, Pepperell itself is a very small part of this grid box. So when I look at my global climate model and find out what's the temperature of Pepperell, I'm really finding out the temperature of a much larger area. And I get an average amount of rainfall, or an average chemistry field, ozone, that really combines all the cities and all the rural areas and smooths it in this one way. So this is partly why you don't hear a lot of regional predictions from global models, because they don't have the capabilities to speak at the regional level. And even though we might know much more about it, they can't process it all. It's not really what the global models are designed to do. So moving on from there, global models, they provide us context. We call them boundary conditions. It's happening kind of on these big grid boxes, but they're not particularly useful for understanding what's happening on the scale of this community. So they try. This is from Big Report, and their regional assessment was just to Eastern North America, including large chunks of the Atlantic Ocean. So this is kind of their regional prediction, which is still not necessarily helpful for you guys here trying to figure out what's happening in Pepperell. Other ones do have a little bit better resolution. This is the temperature response and the precipitation. So how is the temperature going to change, and how is the precipitation going to change? And you can kind of look now and see some of the more detail. You can figure out what's happening in Massachusetts, more or less. But this is also intriguing. This is temperature, and we're certain that the temperature is going to warm. That's one of those certain things. Temperature is definitely warming. But the amount of precipitation change, that's more uncertain. And it's largely uncertain here because we know it's going to be wetter north of us, and it's going to be drier south of us. But we're kind of in that middle band where there's kind of a mix, or there's the transition. And so that makes it very sensitive to the particular way you've run the model, the particular model you choose. What we have here, this is the number of models. They ran 21 models in this case. And this is the number of models that predict an increase in precipitation. So if you look where we are here, we're right about here, and that's about 8 to 13 of the models. So about half of these models predicted an increased precipitation, and half predicted a decrease. That's a reflection of some of these uncertainties I've talked about. It's a reflection of how these models were developed, what's going on. But even these regional models aren't certain about what's going to happen in Massachusetts with precipitation. More of them seem to be predicting an increase in precipitation, less of them a decrease. But we need more research, or we need to kind of dig in further with this. And this is just 21 models. There's many more models that have different pieces. So that's why I'm turning now to regional models. And I don't myself run regional models, but a lot of my colleagues do. And a regional model usually is the Eastern US or New England. That's kind of the zone that they focus on. They use the output from the global models to drive the boundary, the outside of that box, and then they simulate much more detail within it. So I'll be looking now at some regional model output for temperature and precipitation, and then weather events here. And really, for Pepperell, these are hyper-regional and hyper-local. Like, this is even sometimes hard for regional models to get at because it's a small area in general. So this is one regional model. You can see they did the northeastern US. And this is the change in temperature, surface temperature, in winter and spring and summer and fall. And here you can see they're predicting warming in every season, more in the winter, less in the spring. But yeah, warming every season. It seems very likely for this particular model that winters are going to warm more than the other seasons. So that has regional implications for us here. There is a resource here. I could send it out. It's a climate action, what is that? Tool.org. It does give you even more resolution, and you can kind of play with the knobs here and try to zoom in even farther. But this is one example. They could just run Massachusetts. They only did one state here, but they let you see the level of detail that even the regional models can't produce. And they predict this is a warming throughout Massachusetts. These are precipitation changes, and as I mentioned before, we're more uncertain with the precipitation. But this is, again, the seasons: winter, spring, summer, and fall. There's going to be an increase in precipitation in most seasons, especially in the spring, strong in the winter, but it looks like there's going to be a decrease in the summer. Although if you look at Massachusetts, and I'm going to zoom in on Massachusetts, in this model, we're right in between, warming and decreased use. So we're right at that transition where this model really isn't sure what's going to happen here. It might increase a little bit, might decrease a little bit. It's not going to be a huge change in the summertime for precipitation, but it's likely to, well, I don't know, decrease a little bit. And so this is why we need to kind of pay more attention to the developing science in this case, because precipitation is a much more uncertain thing for this particular region than temperature change. I have some others. This is just another view of it, but every regional model has kind of a different answer because they're tuned a little bit differently, or they use different data sets, or they're built by different people. So this is kind of a developing state of science that we're talking about. I showed that one already. Okay. Now I want to talk about weather events, because that's a big deal, extreme weather events. And this is the single day 100-year storm, the amount of rainfall that happens in the New England and New York area. And here we are. So a 100-year storm for us is about 8 inches of rain. That's a lot of rain. Has anyone here experienced one day of 8 inches of rain? Yeah? Okay. All right. Was it in the recent past, or yeah?
Oh, Missouri.
Okay. But that's a lot of rain.
We have a long time ago. I'm trying to remember if it was in the 90s.
Yeah.
Because we had bought our new house on the river, and we were watching it closely. Army Corps of Engineers was watching it.
Yeah, okay. I looked up, and there was a hurricane in 1938 that I think was a big flooding event here. So that was almost 100 years ago. I think we can consider that a 100-year storm event. So now one thing we're trying to figure out is how likely is that storm to come again? 100-year storm means it comes every 100 years, so we're coming up on that place. And then the trick is, if the climate is changing, that 100-year storm is changing as well. But because we only have one every 100 years, it's really hard to predict changes in extreme events because we just don't have enough data. If we could freeze the world as it is and keep it that way for 1,000 years, then we have a really good idea of how frequently a 100 storm event is happening. But
100-year storm events are happening more often.
well, it depends on where you are. Yeah, that's the regions where it's wetter, they're happening more often. And then there's a trick too, because there's frequency of storms and intensity of storms, and those are not happening in the same direction. So I'll get to that in a little bit as well. These are some regional predictions for storminess, and over Massachusetts, it's getting wetter. So on average, there's more rain per year. This is looking into the future under different scenarios, and for almost all of them, it's getting wetter. It might be getting a little bit less wet in the fall, maybe part of the summertime, but in general, it's getting wetter in Massachusetts. This is the storm I talked about. I found this piece talking about the Nashua. Am I pronouncing that right? Reached 9.1 feet, and that was a big flood stage. Does that happen frequently now? When's the last time it flooded?
Early 80s, there was a flood, the bridges were out. I was in Worcester and I had to come back around through the
It
back
flooded
way.
in 87.
87?
Because I know that the house that I purchased had flooded in 87.
Okay.
And then it flooded after that. The house had water around it later on after I sold it in 97.
So it floods every
97 to 99.
floods every decade or every few decades is kind of the frequency of the flooding event. Yeah. So trying to figure out, is that going to change in the future? And that's a tricky question. So I have a few results here. This is from that big storm, the amount of rain that fell, and it looks like, right, is Pepperell in this light blue piece, or is it? Yeah. Right, so it seems like there was not as much rainfall here as in almost the entire surrounding area for that particular storm. I found this figure, these were the location of track and bridge washouts along in the area, and so there's reach up here. So the storm surge from this hurricane definitely affected this area.
38, the covered bridge wash up or something like that. I think I heard.
Yeah, right. The Main Street Reach, okay. So that's kind of the 100-year storm that we can expect. One question that I was asked is sea level going to affect Pepperell? And the sea levels are rising. As I showed before, they're rising slowly. So besides these storm surges that might happen from a hurricane kind of pushing the water up the rivers, sea level is not really a big concern here, not for another 400 years or something. So sea level is not the biggest concern. But this change in storminess is more. These are hurricane trends. These are the different oceans across the globe from the 70s to today. And in pretty much every ocean examined, there's an increase in the number of storms. This one here is also the 70s to present day. This is the number of hurricanes sorted by size. So the blue and the green are category 1 and 2 and 3 storms, and the red is category 4 and 5 storms. So we see something interesting here, that the smaller storms are becoming less frequent, while the larger storms are becoming more frequent. There's not that many storms, so the statistics on this isn't quite as solid as temperature records, for instance. And I'm not sure what happened. There was a big jump here. That might have been a shift in some sort of regional climate. That might have just been, because there's only 20 storms a year, it might just be an artifact of the statistics. But if I was going to prepare for the future, I would definitely think about the frequency of big storm events. That's what I would worry about. And then here's a nice summary I found. You can't see it. This is from the Climate Change Adaptation in New England Agriculture study in 2013. And they had two things here. They have temperature changes and precipitation changes. And so this is the temperature in the past, the previous climate, and we know that it's warming. So we know that the amount of cold extremes is decreasing. The amount of warm events, what was a heat wave 50 years ago, is going to become more regular, just a regular summertime. And then there's going to be some record hot weather, just because we're shifting that distribution a little bit higher. That's the temperature trend. This is the precipitation one, which is a little bit more tricky. The old climate is the outside line here and the yellow line. So the old climate looks like that, and the black line is the new climate, or the projected climate. And we see two different things here. We see first, there's going to be more heavy precipitation. That seems very likely to be what we should expect here, more heavy precipitation, while at the same time, less light precipitation. So and this is where you really need someone. I'm a global scientist. I need someone here to kind of interpret this in a regional way. Does that mean more droughts, or less droughts, or more flooding events from washout? Or this is where my expertise starts to fade, and I need more input here. This is one final way to look at it here. This is, again, the amount of precipitation, the number of extreme events, and the number of dry days for, I believe it's now to the end of the century. So this is what's happening in the recent history, and these are the changes to expect as we go out. And we can see, there is a slight change in precipitation. It's really not a strong signal there on average. It's really negative down here in the southwest. Up here, we seem to be a little bit wetter, but it's not a big trend. So here, the number of extreme wet events, we're definitely going to see, according to this study, more extreme wet events, maybe 20 or 30% more by the end of the century here. And this is the number of dry days. We're seeing, it's interesting. It's pretty strong here, and then it really fades as you get to the coast, because the ocean has different dynamics that affects the coastal weather. So it's likely to be a decrease or increase in the number of dry days, but that's one of the more uncertain things too. So there's, the regional climate's really difficult in this way, that when you drill down, it's very tricky. So this is some of the kind of the big points I was trying to take away in terms of agriculture. How is agriculture going to be affected by regional climate here? And I know that agriculture is sensitive to temperature and groundwater and the seasons and pest populations, and these are all kind of changing under a changing climate. So So I'd say what to expect or what to be worried about. Warmer temperatures, which probably implies, or it does imply a longer growing season, which could be good. But that's combined with more stress on water resources. There's less of that, less frequent precipitation, so drought might be more frequent combined with a longer season. I don't know what that means for agriculture. That's part of a discussion we should have. More heat stress, more of those extreme heat waves will affect crops and livestock. This increased storminess of extremes probably has big implications for flooding in the short term. And then also these warmer temperatures increase pest survival. And this is something that I also don't have, I'm not an entomologist, so I don't know exactly what these different pests are doing, but I'm assuming they're changing. I've read some studies saying that they're becoming more frequent or they're living through the winters. This is where we should probably talk to an entomologist and kind of really get these details out. But yeah, that's my agricultural slide. And then I'm wrapping up here now to get ready for some questions. But really, the particular challenges in pepperell, warmer temperatures, that's something I would definitely expect. Drier on average, probably, but combined with wetter extremes, more storm surges or more extreme precipitation events. That particular combination is interesting. And this is a balancing act then, that you're balancing the longer growing seasons with increased heat stress and the more extremes and the changes in pest dynamics. It's a complicated picture, but that's kind of the global view of your regional climate. And this is kind of the last figure I'll show. This is looking at kind of the average temperature of Massachusetts as we go into the future. And one nice way to think about it is how farther south is it going to be. So here's where we were in the last 40 years. And as we go into the future, our temperature climate is going to be more and more like that of the more southern states, where in this particular case, in the high emission scenario, Massachusetts might be more like South Carolina in 100 years. That's one scenario. Maybe it'll be more like Maryland, but definitely, the warming is one way to think about it. So I kind of like that figure. So I'll end there. I want to thank you. And then here's just the whole slide that I use for the Calvin and Hobbes, just to give you the full context. But thank you. Yes.
I have a broad question.
Yes.
Since you studied more on a global scale and look at that kind of data, I learned it in my environmental health class about a scary catastrophic scenario that could happen with warming oceans, that the conveyor belt could actually stop and then cause an ice age.
Yeah. There's a few of these. And these are, so she asked about the catastrophic kind of events and the likelihood of those happening. There are a few of those that we often call them tipping points, where if you get a state where the entire system shifts dramatically, which has happened in the past, that's a thing where we can make some predictions, but there's still not quite enough information to know precisely how likely that is to happen. We know that it happened in the past, but it involves a lot of runoff from Canada cooling, and it had a big impact there. It doesn't, from my understanding, that's not likely in the near term being 50 years or 100 years, but it might be more, after that, it might be more possible.
It all takes off. We don't do it.
Yeah, or other ones are there's a lot of methane deposits in the ocean and in the permafrost and the northern latitudes, and they're locked in the ground because it's frozen. As the ground melts, it might release more methane, which is a big greenhouse gas. It might release a lot more methane, and that would have a big climate impact. And the likelihood of that is also uncertain. We've never observed it in the past, so we don't really know exactly how likely that's going to happen. But it's a scary possibility that we should be considering.
Can you talk about ocean warming and ocean acidification?
Yep. So when you release carbon dioxide in the atmosphere, carbon dioxide gets soaked up into the ocean, and it creates carbon dioxide bubbles, or it's dissolved. So and what it does there when it gets dissolved is it makes it more acidic. It's just physics and chemistry of carbon dioxide equilibrium in water. And we're definitely seeing significant ocean acidification. It is beginning to affect certain coral communities, or certain the little microbes have trouble building their shells because it's more acidic. And we're seeing some pretty significant impacts of that at this point. And that's one piece. One possible climate solution is to have a volcano every year. It releases sulfate aerosols into the stratosphere every year to cool it just like a volcano would. That's great. That might reduce the temperature change, but that doesn't touch ocean acidification because the CO2 is still there. So, right. I'm not an ocean scientist, but if I was an ocean scientist, I think I'd be very concerned about ocean acidification because it is one of those things that's changing, and it doesn't seem like it's going to stop changing, and we don't know how bad it could be.
Yeah, for fish species
and corals and right, a lot of things.
I haven't heard acid rain since the 80s or 90s. We're still dealing with acid rain? We're not close to finishing the book.
Yeah, we're still dealing with it. S-ray is more close to my heart. That's more atmospheric chemistry. We did a great job in fixing that in this region. You know, identifying the cause of it and where it was going and addressing the emissions. You know, so in this region, it's not a fixed problem, but it's a much better place than it was before, because policy was enacted to deal with the science in a nice, very effective way. There are other regions where acid rain is still an issue, and in the global scale, it is still an issue. But for communities like this, it's certainly not the most pressing issue anymore. Yes.
It's really interesting for you to focus on the regional area in Pepperell, but of course, we're bigger than that. And food sources, for instance, we rely an awful lot on the Midwest.
Yep.
The breadbasket.
Right.
So whatever happens with regional climate change in the Midwest is certainly going to affect us here.
Yes.
And what choices then we might have to make regarding our food resources and where we're going to get our food in the future. And then that could have a specific impact on a town like Pepperell, where we still have agriculture going on. And more and more of us are turning to local community agribusiness instead of, the larger Midwest model. Do you have any thoughts on that? Because that's kind of like planning for the future.
Yeah.
And one of the things is around food.
Yeah, the term I like is resilience in this sense, where if you're looking at the future where there's uncertain events, or we don't know what the Midwest is going to do, or how firm our food resources are going to be, one way to kind of hedge the bet is to make our community more resilient, to kind of have backup plans and alternate resources in case that one fails, we can go here, here, and here. And so that's definitely more on the value side. How resilient do you want to make your community, and how much of a pressing issue is that versus paving the road next year? And that's more of a community level values discussion under a context of uncertainty. That's science can help with that, but that's outside of my particular expertise.
But the science certainly can help.
Right. Yeah.
Discussion about resiliency or independence, or how communities like Pepperell can be part of the future, where we're looking at other ways of developing our food resources.
Right. Yes. Where if let's say we're assuming there's going to be a lot more heat waves, in 20 years. Maybe that's something we're worried about. We can look at the direct implications of that. And if the Midwest gets too bad heat, or like a horrible summer where all their 50% of their food isn't produced, how will that affect us? And science can definitely help with those questions. Given scenarios and giving what ifs, science can help answer those. Yeah. Yes.
Can you talk a little bit about the effects of drought on water supply in this area?
Yeah. I'm not a hydrologist. I had a friend who was, and I was going to ask him more questions about this. But right, if there's continued drought, you get like a decrease in the water table over time, and so that definitely is a direct effect on that. And I think that's the winning effect versus the increased storminess. So yeah, so I don't want to say too much because I might say some of the wrong things, but I would assume more drought, more temperatures, much more stressed water resource here, and I'm not sure what the best way to solve that is. Yeah. Yes.
I think that planning for maintaining wetlands and stormwater management is part of the answer.
Yep.
Because with the severity of storms, you're just going to have that all running off instead of recharging into the ground.
Yeah. Yeah. That makes sense to me. Like that.
I slipped down across the border from New Hampshire. There's a number of forums and symposiums up there. Department of Environmental Services and League of Conservation Voters and maple growers, maple syrup industry, at a meeting in Keene where they stressed that the sugar maples are being stressed and they're afraid that they're going to be sort of migrating north, dying out down here and all that, and trust productive other maple species. The shrimp industry in Maine has been devastated. fish, which their fishermen are catching. We're now seeing more species that typically come from the south. And Fish and Game has had talks about how the moose population is being affected, because with the warmer weather, ticks survive the winter, and they're actually bleeding moose to death, calves in particular. So there are a lot of on-the-ground effects.
Yeah, and it's good to look to the sensitive populations, right? If you want to see, because if some of these changes are small, you want to look to the populations or the ecosystems that are the most sensitive to these changes. So you listed many of those sensitive populations, and that would be a good way to kind of get a gauge for what's happening. That's a very good point.
A quick question about the aging globe. Could it be that maybe what's happening to us while we're here is just the normal aging process for the Earth, factually? That as it ages, it goes through hot and cold like it did millions of years ago? Is that a possibility?
Yeah, I didn't show the slides here, but there's ways we can't experiment on this Earth besides the experiment that we're doing now. So the models let us kind of ask some of these questions. So one of the questions we ask is, what if we put into the models no human emissions? What if it is just kind of natural emissions? What would the globe be doing in that sense? And so you get kind of these cycles, and you can look at them, and they are there. Those natural cycles are pretty well understood. The larger you go, the farther back you go, the less certain, but we have a good feeling for them. As soon as you add in anthropogenic emissions, the change is so much more dramatic. That's part of the confidence that we can't make a model not change dramatically when there's human emissions in it. So that's one of those. It's not a perfect test because we can't experiment on a second Earth, but that's one of the ways that we draw conclusions. So, did that answer your question? Okay.
You mentioned one of the big problems is the coarseness of the models. Can citizen science sort of fill in some of the coarseness, whether it's personal weather stations or direct observations? Can that help?
Yeah, one method for reducing the resolution or increasing resolution is called statistical downscaling, where we know that in this grid cell there's a valley here, so it's a little bit warmer in the valley and cooler here, and we can get this local knowledge of what the actual change is, and we can take that grid cell and then apply that particular mask to it and get a better feel. So that's one of the ways you do get really fine resolution. And there was one figure, I skipped it. Which one was it? Was this one here. This is kind of the grid resolution, and that's statistical downscaling way of doing it, where they said, well, we know that there's these details on the fine level. How does that change kind of the global model? So that is one way. The more local information you have, the better you can interpret some of these global models, and these coarse resolution models. So yeah, definitely.
On one of your slides, you show that with the interventions that we've initiated, which are that's green energy and other conservation efforts, that we make some progress with weathering that slow down.
Right.
What else, what more, there's a lot that needs to be done to actually make significant progress. What are those things?
Yeah, and so I didn't. There's a whole other presentation on what we can do on this, but in a nutshell, the biggest thing I showed, carbon dioxide and methane are the biggest warmers in our system. So if you're looking for low-hanging fruit, reduce the emissions of carbon dioxide and methane. Carbon dioxide, most of it comes from burning of fossil fuels, coal and oil and gas and even wood. So the biggest scale thing you can do on your personal level is reduce your consumption of fossil fuels. Make your home more insulated, or don't drive a car alone as much, maybe carpool, or try to reduce that piece of it. And even though that it's almost unsatisfying because you don't feel the direct impact of one less car trip a week, but on the global scale that does make a difference. Carbon dioxide travels around the entire globe, so if enough people reduce theirs a little bit, there'll be a definite global impact. So yeah, fossil fuels is kind of what I would point to.
Can you talk about how the carbon that we put, and why we don't see the changes till later on, that the carbon that we put in the past is now coming to light, and how what we're putting in now is delayed, and how that all works?
Yeah, so there's two pieces of that. One of it is that the ocean is slow to adjust. So we're in this transient state where, you know, if we stopped emissions right now, kind of kept them at these current levels and didn't change them anymore, and let the ocean equilibrate in 200 years, that would kind of be the total impact of our emissions now. We can't do that, obviously, but we can do it in some models to feel for it. So part of it is that the ocean is just so slow in balancing that's why part of it is slower than we realize. The other part is we're causing small changes on a very variable state. You know, weather's variable. We're changing, you know, 1 degree Fahrenheit or 2 degrees Fahrenheit on something that swings 60 or 70 degrees from year to year. So it's hard to see that signal and that noise. Now we're just beginning to be confident that there is a very solid signal in that noise because we have enough data, we have enough time, and we're changing it significantly at this point. So.
I have a question about trees and their ability to absorb carbon. I saw this online, this young person had the goal of planting 1 billion trees on the earth. Would that help?
Yeah, trees take up carbon dioxide. They hold the carbon dioxide in their stems and trunks, but eventually they die and decompose and release it again. So trees are a storage for carbon, but it's part of a cycle as well. Yeah, so that definitely would help.
I mean, how do you know what percentage, like how much does the ocean absorb versus,
Yeah.
you know, the trees on the earth?
You go to the models, yeah, because the models have all those pieces and all the knobs, and the models should be able to help you answer those specific questions. Yeah. Yes.
I've been in Pueblo for 35 years, and we lost most of the ash trees.
Mm-hmm.
Of course, we lost all the elm trees and whatever. And we have tons of ticks every year the last 2 years. And we have also now the maple trees being
Right.
threatened. So it seems to be with global warming, what's happening. You've got the bugs and the trees, and then you have these bugs that come in for the hemlocks.
Right. Yep.
That have been incorporated, where there used to be lovely stems of hemlocks and around Tower Hill, a big part of Massachusetts. We still have lovely hemlocks here, which will soon be gone.
Yep.
Yes, I see woolly adelgid.
And this is part of what global warming is here in Pepperell. If you lived here a long time,
Mm-hmm.
you see it.
Yeah.
You see it.
And you see bird species
Yep.
that are migrating further north that were,
Yeah.
you know,
And I'm a big bird guy. Birds are complicated because they make a lot of decisions. The temperature is one of them, but also food availability, and you know, so birds are complex. The 30 years of changing tree patterns or pest patterns, that's the climate scale. You know, 30 years emerges from that weather variability. So that's a better way to think about it. You know, if the last 3 winters are warm, maybe the ticks go crazy. That might be a weather event or a weather signal, not yet climate yet. But that's, you know, yeah. Yes.
Has anybody studied various tipping points and which ones were already tripped and we can't recover, and which ones are we about to trip, like the permafrost and methane and CO2 and,
Yeah.
and the ice in Greenland, etc.?
Yeah, a lot of the climate studies that do that, it's more paleoclimate, looking at the long-scale climate changes. And the trouble with that is to run a 1,000-year climate simulation, you know, you have to go course through, or your time resolution is decades, you know. So there is a lot of knowledge about that, but then trying to predict what's happening in the next 10 years, or, you know, it's the same sort of resolution problem, but more on a temporal scale. So one thing is we know these things are possible. They happen in the models when we push it too far, but each model behaves a little bit differently. And so when we add the same forcing, you know, this one happens next decade, and this one happens in a century, and there's kind of everything in between. So that's one of those uncertain things that we need more understanding of before we can state what's happening.
I mean, we keep hearing that scientists' projections are not, they were off on the projections, and things are worsening, like for the polar ice caps like in Greenland or whatever, much faster, and the Antarctic shelves and whatever, and the permafrost. So when you update your models, with that information. I wonder how that,
Yeah, and that's the edge of the certainty circle, right? When we get more information, then we have a better idea, and that's changing all the time. Yeah, so like the ice extents or the northwest passage, that's still an uncertain thing where the models behave differently, and depending on what you put into it, you get a different answer. So that's still cutting edge science in that sense. That needs more work. But yeah, pay attention to those studies, even though those studies tend to be one model predicting this one thing. Sometimes they're multiple model studies, but right, it's still a variable. So.
We'll do 2 more questions.
There is a book called 6 Degrees. It was written in 2008, so things have changed a bit since that time. But the author was very hesitant to predict on a time frame what the changes might be. We based the whole thing on if the temperature increases 2 degrees centigrade, you'll see this. If it increases 4, you'll see this. But then he was very hesitant to nail
say
a
when.
date.
Yeah, and part of that is yeah, the Earth system changes slowly and we're transient. So if we can kind of keep it steady, then we'd have a better idea. But because we are changing in a lot of ways, it's a transient system. Any other questions? Yes.
Is there any science, possibly like psychological science, on how to talk to other people to kind of get them to better understand? Because there's obviously a great deal of people that don't even think that this is real. So is there any science on that and studies on that, how to actually talk to people about?
There are fields of science about that. Yeah, yes, yeah. I have a friend who studies risk perceptions of natural disasters, and so he studied in Pennsylvania perceptions of fracking and whether fracking was good or bad, and it depended more on political leanings than how much information you were given. And yeah, this can be a whole other talk, but yeah, there definitely is. So, all right.
Brain transplants.
Thank you.